Okay. Oh no. Okay. Wait a second. I think it's fine. Yes. Okay, so can you hear me? Everything's fine? Great, thank you very much. So thank you, Elizabeth, for the kind introduction and for the invitation to visit you here and to talk to you. Today I'm going to talk to you about single photon generation, storage, synchronization, and towards interaction in hot atomic vapor. And it did work before. Yeah. So I'm from the Weizmann Institute in Israel. It's in a town called Rehovot, just a bit south of Tel Aviv. It's a research institute, so not a full university. It was founded 1934. Only graduate students in only biology, chemistry, maths, and computer science. They're touching. All right. So we'll do that. No problem. Thank you. It's relatively small, only 300 research groups, 1,000 students, 500 postdocs, and about 200 staff scientists like me. Cool, thanks. And these are some views from our institute. This is the old accelerator tower. It used to have a vertical particle accelerator in it in the 60s, not anymore. And this is the physics building. So you're all invited if and when you come to Israel to visit us. I'll be very happy to host you. Okay, so I'm a part of the group of Professor Ofer Furstenberg, and our group is informally called Light versus Matter. And basically what we're trying to do is to do quantum optics with atoms. And we have basically use atoms to control light at the quantum level. So we have three main research projects. The first one is achieving strong photon-photon interactions in a Rydberg excited cold rubidium cloud. And Ofer had a very nice virtual AMO seminar about that about 2 weeks ago, and I highly recommend it. The second project is quantum light generation and manipulation using warm rubidium vapor, and this is what I'm going to tell you about today. The third one is long-time storage of light in mixtures of alkali and rare gas. I'm not going to say anything about that, but you can ask me if you want. Later, we also have a few new projects that we're just starting. We're studying new solid-state systems for coherent light spin coupling. We are now building a tweezer array to trap atoms, single atoms in tweezer to study complex light-matter interactions. And we're also thinking of building some experimental demonstrations of some interesting quantum thermodynamics effects. Okay, but today I'm going to talk about this. So, what is the goal? The goal is to control the quantum state of light, but more specifically, build complex entangled states of light bottom up. So, the main applications are in quantum communications, like you have those repeater states that can do error correction, and they have to be of some very sophisticated entangled states. And for quantum computation, for example, in one-way quantum computation, when you have cluster states that you measure, and that's how the computation goes. For quantum metrology, if you have entangled states, they can be much more sensitive to external perturbations because of the entanglement and rich sub-shot noise sensitivity. And also for foundations of quantum mechanics, how big can we make an entangled state? Is there a fundamental limit? We don't know. We need to make those states first. So how would we go about making those, building those complex photonic states? So we need single photons. So we need an array of single photon sources. But usually single photon sources are a bit probabilistic. You don't know when, so a photon can come out randomly. So you get a bunch of disordered photons. And we would like to order them. So we need something that would order them. And this can be done in time. It can be done by quantum optical memories, which are devices that can store a photon on demand and release it on demand. So it can basically take those disordered photons and with some classical information from the source about when exactly each source fired, you could feed that forward into the memory and tell the memory to release the photons in such a way that they will come out together. So now you have ordered photons. And then the third thing you need to do is to induce some photon-photon interaction. So the photons would feel one another and would basically communicate within themselves to create an entangled state. And we think that hot atomic vapor could be used for all of those three steps. For the first two, we use the photon-atom interaction. And for the third one, we can use the atom-atom interaction that with the photon-atom interaction together, they basically create an effective photon-photon interaction. So when I'm talking about hot vapor or a system, I mean this beam of light, say in a quantum state of some amplitude alpha of no photons and amplitude beta of 1 photon, let's say, entering this vapor cell and exciting a single atom in the vapor cell, or not exciting at all, right? Because if it's in the 0 photons, nothing will be excited, so you'll get this state. And if it is in the 1 photon state, 1 atom will get excited. But we don't know which. So they are in a superposition of one of all the atoms to be excited. All the possibilities are here. And so it could be this one or that one or that one. And the amplitude of every element in the superposition or the bunch of amplitudes here are called a spin wave. They basically, you can look at that function as the function of the position, right, as a wave of excitation. And why is it called a spin wave? Because usually that excitation that I'm talking about is a spin excitation. And this is because those excitations are long-lived. So people have used them for many years to do these things. But actually, it doesn't have to be a spin wave. It can be any excitation wave. This excitation can be of any other sort. For instance, it could be an orbital excitation, where one of the atoms is excited from the ground state to some highly excited state. And this is what we're going to use here. Okay. So I'm going to tell you about our spatially multiplexed heralded single photon source, our noise-free quantum memory for light. Both of them are with warm rubidium atoms based on the same 3-level ladder system. And then I'll show you how we combined the two and synchronized two photon sources using the memory. And then I hope that I'll have time to tell you a bit about our efforts towards observing photon-photon interactions using excitation to Rydberg states in those warm vapors. So I start with the source. So in the source, we have the levels of rubidium, 5s, 5p, and 5d. And we excite from the s to the d using two lasers, one at 780, one at 776. They are counter-propagating, and they are continuously on. And what they do is create coherence between the S state and the D state. And this coherence is rather long-lived because the wavelengths of those two lasers are almost the same, and we put them into the system from opposite directions. So the wavelength of this two-photon excitation would be the frequency would be the difference frequency between those two frequencies. It will be a very low frequency, so it will have a long wavelength, about 150 microns. And that means that it survives atomic motion for a rather long time, a few tens of nanoseconds. So this coherence, this created coherence now has a few tens of nanoseconds, which is more than the spontaneous emission lifetime, to spontaneously emit two photons. So once it's doing that, these two photons are correlated because they're emitted at the same event. So if this one is emitted, the next, there's very high probability that this one is emitted too. So we use this photon as the herald. So we detect it, and once we get a click on the detector, we know that we have a signal in the other port. So this is our heralded single photon source. And ideally, if our vapor cell would have been a kilometer long, and the photons would have, due to conservation of momentum, they would have been emitted only along the axis. But since our cell is just a few centimeters long, the conservation of momentum is not perfect, and we get a bit of photons coming out from the sides, just at very small angles, like a degree or so. Yes? Not by much, no, because these two wavelengths are almost the same, and also they are parallel to one another. Then the phase matching condition is on axis. But the phase matching is not perfect. So the phase matching is another word for momentum conservation, just in wave language. And we get some photons coming out from the sides, just a bit. So we take a sharp mirror and just look at those photons that come from the side. And now we have one source here. Okay, so if we detected a photon here, its partner photon will come out at that direction. And if we detected a photon here, the partner photon will come out at that direction. So we basically multiplex spatially and have two, or potentially more, but currently we only have two, sources just on the same, with this, using the same vapor cell. And our student, Omri Davidson, is the person who built this system and brought it to near perfection. And a lot of details about that are in this paper. Okay, so I'll just walk you through our main results from this source. So first of all, we just operate one of the sources and measure the probability of getting the conditional probability of getting a photon out if we measured a Herald photon. So we want to know how good is the correlation. But what is the ratio between correlated photons and just accidental photons? And this is what we get as a function of the time between those two events. And you see that here around 0, we have a peak of about 700. And 700 here is with respect to the number of coincidences that we get at very long times. So the correlated to accidental ratio is about 700. So pretty good. Next, we want to know whether the photons that are emitted are indeed single photons. So we measure the autocorrelation function of the signal photon conditional on the detection of the Herald photon. So we herald a photon, we know that we have a photon here, and we check whether it's just a single photon or two. So what we do is look for the number of coincidences at a certain time window around 0. And we increase that window size. So you can see that, okay, when the window is closed, we don't get any events. So of course, we also, sorry. Is that too much? Too many times? Okay, so, but when we opened it, let's say to this point, about 2 nanoseconds, we get most of the events, right? So about 95%. And still, the ratio of getting a double click to not getting a double click is about 8%. So this measures how many doubles we get. So a few percent. And that also depends on the pumping rate and so on. We can control it. I'll show it in a minute. And the last thing we want to check is whether our two photons are indeed indistinguishable, because for building these complex states of light, we need to interfere the photons, and they won't interfere if they are distinguishable. So we need to have indistinguishable photons. So we do a heralded Hongu-Mandel experiment. So we herald on the event that we got clicks in both of those detectors and put the signals on a beam splitter and measure how many double clicks we get here as a function of the time between the clicks here. Okay? But they are conditioned on 2 clicks here. So this is a 4-click experiment. Okay? This is a 2, 3, 4. And this is what we get. This is the, looks like a standard Hongu-Mandel diagram. This is the time difference in nanoseconds, and this is the normalized coincidence rate. And you see that near 0 it drops down, which means that they interfere well, right? So they are well. When they arrive together, they are indeed indistinguishable. I will elaborate on the distinguishability, the residual distinguishability later. Yes.
Can you try to just measure the G2 of 1 arm?
That would be thermal. You'll get 2. So
obviously you don't have many modifications because you haven't.
Yeah. So I'm not sure whether we actually measure that. I'll need to check. But ideally, if your photons are indeed single mode, and you basically trace out this detector, and there's perfect correlation between them, then you'll get thermal photons, meaning that the G2, the correlation function of 0 would be 2. But if there are more modes here, then you'll get less than 2. I think it's quite close to 2. I'll definitely check. Yes, thanks. Let's continue. And as I said, there's a noise rate trade-off. So this is the rate of emitted photons in kilocounts per second. So we can get up to 400 kilohertz of emitted signal photons, heralded photons, so 400 kilohertz of double clicks between the idler and signal. But then we look at the G2, so how many doubles we have, and we see that it goes from very close to 0 to not so much 0. So we need to choose somewhere in between to optimize both for the rate and the doubles contamination. The same thing goes for the accidentals. So this is the peak to this normalized signal idler correlation peak as a function of the generation rate, and it also goes down. So that means that the relative amount of accidentals goes up. So again, we need to choose. But you look at the absolute values, we're in a very good place. So this and that are this and that, the same graphs, and all the points are other photon sources at the gigahertz and less bandwidth, not the terahertz ones. And we're doing quite well. There's only one, at least at the time of the paper, was published about a year or so ago. There's only one cavity spontaneous down conversion source that was a bit better at a certain regime. But of course, we can go to higher counts if you want to, and so on. Okay. So the source is not bad. And in particular, it fits, it uses rubidium. So it naturally fits the rubidium memory that we also have. So now I'll tell you a bit about the rubidium memory. This is Ran Finkelstein, Dr. Ran Finkelstein. He graduated. He's now doing a postdoc in the group of Manuel Enders in Caltech. And he was the main student on this project. And that is the paper from 2018. And when you have a memory that you want to use to synchronize photons, first of all, you need to know some things about the memory. So the things you need to know about what is the pulse, the minimal pulse duration you can store, so the inverse of the bandwidth. You need to know for how long you can store it, and you need to know what the efficiency is. And then the figure of merit for synchronization is this number that we call the effective fractional delay. But in effect, what it gives us is the on-demand photon generation boost, because it gives us the number of successful photon generation attempt while we store a photon. So we have two sources, right? One shoots, we store it. Then try many, many times, as many as we can, to have the other one fire, right? And once it does, we release the first photon and they come out together. But how many times do we have to try while the photon is waiting there? It's this number. Right? So this is basically the figure of merit that we would like to maximize. Other memory schemes may like to maximize other figure of merits, but this is the one for us. And when you want to synchronize more than two, right, it exponentially grows with this factor. So it's very good to have a large, much larger than one factor here, so you get a very huge boost in synchronization rate. Okay, but another very important figure of merit is the noise. Because if you have this memory, there are many atoms there, they are hot, you don't want these atoms to emit photons that you didn't store, because those photons would be thermal and they won't interfere and they basically would ruin your state. So the figure of merit for that is what we call the mu1. The mu1 is the number of noise photons per storage attempt without any signal in, divided by the efficiency. So it's basically the number of unwanted photons out divided by the number of wanted photons out, right? So it's the relative noise that you have. So we want to minimize that as far as we can. You see that the efficiency enters in both, and so it's good to have high efficiency. And by efficiency, I mean the total efficiency, the end-to-end efficiency, not just the efficiency of the storage or retrieval or both process. The efficiency that includes all the fibers and all the mirrors and the windows of the cell and everything, right? So that's the efficiency that enters here. Okay. So the traditional approach to having atomic quantum memories is to store on the spin states. So you pump all the atoms to one of the spin states, and then you couple that state to the signal, and you couple the other state, the empty state, to the control. And via two-photon process, you get an excitation of one of the atoms to the other spin state. So this is all good because it gives you a rather long storage time, microseconds, sometimes milliseconds, sometimes even seconds, if you try very hard, but it has some disadvantage. The first disadvantage is that usually you have to flip a spin here. Well, you always have to flip a spin, but usually you also have to flip a nuclear spin. Flipping a nuclear spin requires the hyperfine interaction, and that is quite slow on the rate of a few gigahertz in atoms, so it limits the bandwidth that you can store. And also, if you want to store large bandwidth, right, then you want to get away from the inhomogeneous broadening here and do this process of resonance. But if you get away too much, right, more than this splitting, then you can have a competing process, that is a four-wave mixing process, that happens when the control couples to the full state. And then it can scatter spontaneously a photon and create this spurious excitation that is in your medium without you putting a photon there. So when you try to retrieve, you retrieve a noise photon, right? That's not good. It's called the four-wave mixing noise, and that was the main limiting factor for high bandwidth lambda scheme or spin-based memories. Okay, so what is the solution that we have? The solution is invert the scheme. We call it FLAME or ORCA. I'll explain the acronyms in a minute. So instead of having a lambda scheme, do this. So instead of storing on the ground state spin, store on a doubly excited state. And it's the same process, right? Everything is prepared here. The signal is coupled to this level, and then the control promotes it via two-photon absorption to the doubly excited state where you store it. So this is we call it the fast ladder memory or FLAME. And in Oxford, where it was invented, actually by Chris Kaczmarek, Josh Nunn, Amir Feizpour, and I was also there, around 2015. It was called ORCA, off-resonant cascaded absorption. I think I like FLAME better, but you know. And those guys, Chris and Josh, now have a company called ORCA Computing that in London with a few other partners that is trying to use such memories to enhance photonic quantum computation. So why is it so good? Why do they have a company? Well, it is fast. You don't have to flip any spin. You can pump all the spins to the stretch state and use polarized light, and you only change the orbitals. You don't change the spin. So you're limited only by the optical frequency differences here between these levels. So in principle, you could go up to terahertz, in principle. It is noise-free. This forward mixing is gone, because in order to create spurious excitation here, you need to have spontaneous absorption, not spontaneous emission. And spontaneous absorption of optical frequency photons at room temperature is e to the minus 40 less probable than spontaneous emission. So it never happens. It also has high end-to-end efficiency, right? Before I stressed that this is a very important figure of merit, because there's no need for tight spectral filtering. In these spin-based memories, in order to get the control out of the way, right? It is just maybe 9 or 6 gigahertz away from the signal. So you need to put it in a series of echelons to filter out, and then that brings the efficiency down. Here you don't need that, because you can just use Sembrock filters and it's fine. It works fine. And another advantage, which is important for us, not so much for a regular memory, but for a nonlinear memory, is that from this state, we can now promote the excitation to a Rydberg state. And in a Rydberg state, it might interact with other excitations and render the memory nonlinear. Okay. So this is from the original paper. This is the system signal and control counter-propagating. Signal gets out. This is a storage diagram. This is time. And this is the intensity. The blue is a control. The red that you can't really see is the reference signal. Means, okay, this is without storage. And this one is with storage, but it's times 2. So imagine that it's half. Right, so this is what's left after you try to store. And this is what you get when you retrieve. And we can run that with many time differences and get this. Right, so you see that we can store for almost 100 nanoseconds, and our pulses are about nanosecond and a half. So you might ask yourself, well, the storage time is the coherence time of this coherence, of this 2-photon coherence. So spectrally, it would look like a narrow resonance. But on the other hand, these pulses are short, much shorter than the coherence time. So they'll be much broader than the resonance. So how can I efficiently store a broad pulse on a narrow resonance? And the answer is that it's dynamical, right? This description of the spectroscopy is true in steady state. It's not true anymore when you're dynamically changing the parameters of the system, like the control field. And so if this is your resonant frequency, when you turn on the control during the control pulse, it's doing something like that. Because it creates a dynamical Stark shift that shifts basically scans. It's a heuristic description, but you can use it to visualize how come you open a large bandwidth for storage. So basically you have this bandwidth and not just the very narrow bandwidth of the resonance. Okay, another evidence of broadband storage is when we don't pump the atoms. Yes? Can you go back one? Yeah, of course. Yeah.
What's going on with all that oscillation?
Yes. So when you don't pump the atoms, right, you have a chance to, with the same polarizations, to excite to both hyperfine states of the D11. And since the Difference between them is about 26 megahertz, which is less than the bandwidth of the pulse that we stored, which was about 10 times larger. We store on all of them. So when we try to, when the coherence is there, it is beating with itself and creating those oscillations in the frequency, in the efficiency of storage. But then when we pump it, then it fixes that. And the reason there was a bit of oscillations in that data is that in order to reduce the noise, we had to stop the pumps before storage. So we had imperfect pumping. We now fixed that, and we don't need to do that anymore. So it's much better now. Okay. Our memory lifetime is limited not only by the 300 nanosecond lifetime of the doubly excited state, but also by motional decoherence due to both Doppler, which is longitudinal motion across the wavelength of the excitation, and time of flight, which is transverse motion across our beam, to about 120 nanoseconds. So we get about 86 nanoseconds in total. And in Flame 2, which is a paper that we are about to submit very soon, we got this a bit better. So how good is it? So this is what's important, right? So it was about 12, which is already good, and now it's about 30. The noise was 10 to the minus 4, now it's a bit below 10 to the minus 4. And this is a big diagram that shows where we are with respect to the other contenders, or the other quantum memories. So this is the noise to signal ratio per photon out, going from high to low. So this is good. And this is the projected rate of 6 photon events per minute, right? Theoretically calculated using Josh Nunn's formula. If we had a certain memory, 6 memories trying to synchronize 6 photons, how many 6 tuplets would we have per minute? So we want this to be high. Both are logarithmic scales, and I focus on this region, which is the low noise region. And here we're doing quite well. This is 2018, this is now. And actually there are only 2 memories that are doing better, and both of them are storage loops that don't use atoms at all. That's why they don't have any noise. And but the slight disadvantage is that they cannot store completely on demand, right? Not at any time, but just at integer multiples of the round trip in the loop. And the best of those 2 is actually here in Paul's group. But our source is continuous, so we use our memory. And so can we merge them and combine them together? So let's first look at just putting those photons in the memory and just storing them for a given time, fixed time tau, and see what we get. This Ohad Yogev is a master's student who was also contributing a lot to this work. And this is the storage diagram that we have. So this is without storage. This is how the heralded photon looks in time. So this is with respect to the heralding click. The photon is an exponential shape. And then with the storage on, almost all of it is gone. And then after a while, we try to retrieve, and we retrieve a bit of it. We also change the shape, which will affect the Hongo-Mandel interference. I'll show you in a minute. A bit, but not much. It looks like a very different shape, but it turns out that it doesn't affect much. And this is the storage curve. This is end-to-end, and we get to over 25% end-to-end efficiency with those photons. And storage time of over 100, 1 over E, over 100 nanoseconds. So do the single photons stored remain single photons after storage? So we measure the G2 of 0 versus storage time after storage. And we see that it is a bit higher than before storage, but it doesn't at all depend. It's still very low, and it doesn't at all depend on the storage time. And we can up to 100 nanosecond, which is the time, the maximum time that we use for the synchronization process. It's perfect. And then we want to synchronize. So in the synchronization experiment, we operate both sources. And once we get a click from the first one, we tell the memory store it. And then we keep trying. We get a click from the second one, we tell the memory, now retrieve the first one. And then both of them come out together. Okay, let's see, how does that work? So this is the 2-photon rate. So 2-photon here is actually 4-fold coincidences, okay, because every photon is heralded, versus the single-photon rate of each source. They both have roughly the same rate because they are pumped by the same lasers. And basically they see almost the same optics, so they have very similar rates. So without synchronization, you see that this goes from 1 per second to maybe a few tens per second. But with synchronization, it goes from few tens per second to over 1,000 per second. So we get a factor between 30 and 10 increase. So this is working. This is actually working. And what about the indistinguishability after storage? This is with the memory, without the memory is the blue. So the distinguishability here, 4% is due to detector jitter, 4% due to doubles, and just 4% actual distinguishability. But that's before storage. And after storage, there's 10% further distinguishability due to the temporal shape mismatch induced by the memory. But this could, in principle, be fixed by shaping the retrieval pulse to get an exponential photon out. And what's very important as well is the rate. So per point, if you sit on this point and you wait for data, for the blue dots, you'll have to wait for 50 minutes. But for the red dots, you'll have to wait only for 30 seconds. So that's nice.
Is the shape change?
No.
As long as you delay anything,
Yeah.
the shape is always changing.
It's always changed the same because it depends only on the retrieval pulse, the shape of the retrieval pulse. I think it's transform limited because it's carved from a very narrow laser, and there's no reason that it won't be. The exponential decay. I think that one is transform limited as well. I think it's related to basically the atomic decay, including the Doppler dephasing. Yes. Yeah.
Which would imply that it is transform limited, doesn't change.
Yeah.
Also, that width is smaller than the width of the
Um,
photon. Like 3 nanoseconds.
Oh, the width of the actual photon was 1.4 nanoseconds. Half width, half maximum, full width, half maximum.
Okay, so then it does match the width of the actual photon.
I think so, yeah. I think so, yeah. Kind of match it, yeah. So we were actually a bit surprised of how small a change it is. But when you calculate the overlap, this is what you get. Okay, Do I have more time or not? Okay. So just at a glimpse. So, so now that we can store photons and we can even synchronize, can we do something with them? And what we want to do is to create interactions. And in order to do that, we need to promote them to the Rydberg levels. So we need another laser around this nasty wavelength. Right. So the levels that we want to work with are a specific level, 38p 3/2. And the reason is Forster resonance. Accidentally, this level has higher interaction, stronger interaction than the other levels. This is from the theory, from calculating it, but we hope that well, it calculates well for all the other atoms, so we hope it calculates well also for this one. So this specific level is expected to have stronger interaction. Okay, but since we're dealing with hot atoms here, we have to work fast. And working fast means that we need a very high Rabi frequency in our coupling laser. That means that we need to focus the beams. And we also want to make the interaction volume very small, right? So to have all the photons filling one another within the interaction volume. So the interaction radius here is expected to be a few microns. And so we focus down to about 10 microns, and we use a very thin cell that is of the length of also a few tens of microns. So the entire interaction volume is very small. Of course, okay, this creates a few problems, but even before that problem, and it means that our memory here will be just a few nanoseconds because the atoms would hit the wall very fast. But fine, maybe a few nanoseconds is enough to get interaction. But there's another problem. When we introduce this 1250, we introduce a strong Doppler dephasing because we introduced extra wavelength, right? Very short 1 micron wavelength for our excitation to the Rydberg, right? So the Doppler time is about a nanosecond here. So even if we can store for 5 nanoseconds, everything will be dephased after 1 nanosecond. So what we want to do is to rephase it. We want to have a very short pulse that coherently excites to Rydberg, so shorter than a nanosecond. And then we wait, there's Doppler dephasing. We excite down and excite back up with the opposite direction. So we reverse the K, right? So the phase accumulated in the first half is K times V per velocity V of an atom. And in the second half is minus K times V. So they would cancel out, and then you could bring it back down and retrieve it. And then we would measure the efficiency, and we would like to measure that efficiency function of the number of photons we put in the pulse and see if it matters. Okay, so this is what we want to do. And it would depend on the number because there would be interaction-induced dephasing as well. Not only the Doppler dephasing, which we can fix, there would be interaction-induced dephasing between the photons, right, due to interaction, because the interaction energies are not the same when the photons are moving, right? But that we can't fix that. That's a nonlinear dephasing that we can't fix. So we cannot fix, but we don't want to fix it because this is the entire effect that we want to measure, right? So, but for that we'll need a very special light source at 1260. It needs to be very strong, very short, not too short, and and have a controllable phase because we want it to be coherent. So I built a Raman fiber amplifier to amplify diode lasers at 1250 that we carved pulses from. It took 2 years of my life. So this is basically using this phosphorus resonance in phosphorus doped fibers. that can shift 1080 pump to 1260 nanometers, basically amplify the signal that you put in there. So this is the pump pulse, this is the signal pulse, you see the 0.4 milliwatt, and then at the output you have 600 watts. So it's not bad. And actually that's not the record is 90 dB. My record in this system is like from about, let's say, I think it was a microwatt to a kilowatt. Bad. But there is a problem. The pulses are strong, they travel through glass, they self-phase modulate. So when you increase the power, you get this distorted spectrum, and when you do Gershberg-Saxton, you see the phase is a linear chirp of the frequency, of the instantaneous frequency. So we can fix that, because we can put a phase pulse, right, as well, with our electro-optic phase modulator to pre-compensate. And from this spectrum, we get this spectrum. And from this phase, we get that phase. And that is in 1 kilowatt. So it works. And what we did with it at the moment, what we managed to do so far, is to measure the retrieval efficiency as a function of the power of one such pulse. This is my last slide, and we see that indeed it's not very good to begin with, right? But it goes down, right? But then it goes up again. And that means coherent excitation, because this is a Rabi flow, right? So we managed to coherently excite to the Rydberg state. This is the same, just in different detunings, and it does what we expect of it. And our student, Chaim, is working towards having 4 pulses, 2 from each side, and doing that experiment. All right, so to summarize, hot atomic vapors can be used for single photon sources and quantum optical memories, and we can combine those to have synchronized photon sources, and they could also hopefully be used for photon-photon interaction, but this is work in progress. There's still much more to be learned here, and I would like to thank Ofer's group. This is Ofer and all the people, the funding agencies, and of course you for listening. Thank you very much.